And this morning we have the great pleasure to have our first invited talk by Prem Devambu from University of California, Davis. Prem is very well known for introducing the notion of software naturalness, or question of whether software is natural. And this is something that he's also, in fact, going to tell us about today. So I think it's a very appropriate topic, and we have a great privilege to have you here at this workshop.
Thank you. Thank you for the introduction. Thank you for the invitation. So what I'm going to talk about today is basically kind of questioning an assumption that underlies a lot of the work that we started in Davis in 2011. So before I get into the details, just disclosure, most of this work was done by students, and in particular the work I'll be talking about today was done by one of my current students, Casey Casalnuovo. So this talk is really about questioning assumptions. So this work we did at Davis started with the observation that software is highly repetitive. And you've seen lots of data on this. Plenty of papers have kind of exploited this observation. Just to sort of reinforce it, so just comparing English and Java. For example, the Brown corpus in Java, I can see the zip distribution of unigrams, bigrams, trigrams, 4grams. So software is highly repetitive. Java here is highly repetitive, and in fact, much more so than English. The best models right now for English are somewhere in the order of 5-6 bits per token, and for software, we get really good language models down to like 1.4 bits per token. So there's very little information in any token of software, and it's highly repetitive. And this means that any algorithm that relies on language models, anything that does beam search, for example, works very efficiently because there's really not that much to search through. The models are very, very good. They can predict what's in the data very well. So this is the observation that we made, and we sort of glibly made this assertion. Software is natural, right? And I'll explain what I mean by that in a minute. But we didn't question this assumption, and so what we've been doing right now is a series of experiments trying to shed light on this question. I don't think we answered this. Is this assertion really true? So what do I mean by that? Basically, the idea is that human speech and writing evolved to satisfy natural human needs for reproduction, for taking care of our young, for finding food. And it helps us to collaborate well with our other people around and take care of our young. So it evolved for those reasons. And the assertion we made is that software is also similarly natural, in the sense that software actually also works the same way. So human language is designed to communicate efficiently in the presence of danger, in the presence of noise. So all this high repetitive nature of the language helps us communicate more efficiently. So we choose to communicate inefficiently so that we can deal with noise and danger and all that, right? So the assertion we made is software is also similar, and we never actually tested that assumption. We know it's repetitive, but why? So that's what this talk is about. So, there's reasons to believe that software is repetitive for the same reasons that natural language is repetitive. And just as an illustration, right? So, in a situation like this is where natural language's repetitiveness is really helpful. You want to communicate very efficiently in the presence of danger to either the person sitting in the pool, or the person in the pool is going to communicate to maybe his kids by the side of the pool in an extremely efficient, noise-resistant fashion that danger is right nearby, right? So why would this argument apply to software? Well, it's not that hard to imagine, right? So most code is written under conditions of duress. And so when people are writing code, they're trying to do two things. They're trying to write code that is very familiar to them, so they don't have to think too hard about it. They're just going to write it as quickly as possible to do the job that needs to be done. And furthermore, they're also thinking about themselves in the future, right? So they're thinking about, I'm going to have to read and maintain this code later, so I want to write it in a way that is very efficient for me to read and understand. Okay, so the argument is like when you read code, you don't want to follow through denotational semantics equations to figure out what it's doing. You want to instantly recognize it the same way you recognize a tiger on the wild or food in the wild very quickly and efficiently, right? So that's what the argument is that makes software natural, and that's what I'm going to try to convince you of. Probably not very successfully because it's still ongoing. So this is sort of very much ongoing work. But that's sort of the intuition behind why we think that software is repetitive, right? Okay, so this has been said by much more distinguished people, Don Knuth. So that software is really primarily an agent of a means of communication. And Earls, another distinguished person, said this yesterday in his talk, that software has two channels: one channel for execution, another channel for human-to-human communication. And so the argument I'm going to try to make is that the reason why software is so highly repetitive and amenable to statistical modeling is the second channel, because software is also a means of communication. So source code itself is a speech act. We're actually talking to people when we write code, and that's why it has all these nice properties. Okay, so right. Okay, so this line of work, when we started engaged in this, and we got very excited because there's like lots of important questions that come out of this. The question we're going to address today is sort of a scientific question: is software really natural? That is, it rises from the same human impulses as speech and writing. The other question, of course, is what can we do with this? And I guess that's what most people here are excited about, is like the applications of this. But this talk really is more on the science, like why is it this way? Right, okay, so just some preliminaries, right? Before we get into arguments about what the reasons might be that software is so repetitive, just to rule out the obvious things. Is it just Java that is like this, right? Is it just Java that's so repetitive? Is it just the design of Java? Import something, 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 throw new, open paren, new this, that, semicolon, close paren, whatever. So is it just Java that's like this? Well, okay. So that's easy to check, right? So you collect several corpora and you do the same kinds of plots. And well, sure enough, it's not just Java. So one interesting observation for all you functional programming fans is that Haskell is the least repetitive of all the languages. I love Haskell. I teach functional programming. I'm the only one who teaches Haskell at Davis. But it is, it may be because Haskell really promotes reuse. It's really designed for that purpose, high level. The data types are designed to promote reuse. And the other joke I like to make is that Haskell really promotes information hiding. Because you don't have, even if you reveal the source code, it still promotes information hiding. So it's not just Java. All programming languages are really different from. You can see the distinction between all of those and brown corpus, which is a varied corpus of English. Okay, so that's one obvious question. We can rule that out. The other obvious question is it just English, right? Well, it's not. Okay, so again, here's a group of natural languages. So it goes bottom to top. The colors match up for those like me who are colorblind. So it's Spanish, German, English, and then a big gap, and then Haskell and the rest of the programming languages. So it's not just the nature of English that makes this repetitive. It's all natural languages are similar, and all programming languages are similar. So there's something about the way people choose to write code. Well, that's the argument I'm going to make, but there's more coming. There's more possible objections, more null hypotheses. So we'll get to.
Because the diagram appears many times, could you just explain the axis?
I'm sorry. I just assumed everybody is familiar with ZIF plots. So sorry. Okay. So basically, this is it's a log-log plot. The x-axis is the logarithms of the frequency. So and the y-axis is the proportion in the corpus. So the most frequent token occurs around 1%. Of the corpus. Okay, and then the ZIF plot, shows you that it's very skewed, right? It's like the few tokens count for most of the corpus, and that very skewed nature. Here we're talking about trigrams, shows that the code is highly repetitive, right? And this is what gives the language models an ability to model the corpus because they can predict a lot of the tokens. Yeah.
Sorry, what's the trigram?
Sequence of 3 tokens. Okay. Right. Sorry. I assumed they've seen all this stuff before, so I didn't belabor it. But sorry. Any other questions about this? Okay, so this is what allows you to use language models to capture the code and do so very efficiently. And they're sort of the measure that's used to see the efficiency of a language model is cross entropy, and so this is the latest kind of model that was developed at Davis that works very well for code. By the way, you can download that model. It's called SLP-Core. It's on GitHub. It's to our knowledge the best performing model for source code. That it's not syntactic, it's purely a lexical model, but it's per token, it gives you the best performance.
So just when you say per token, in a programming languages, there are slight variations in how you define tokens, so identifiers are distinguished.
Yeah.
Are they distinguished?
No, not in this, it's just everything is considered as a token. But I'll talk about...
Every identifier is the same.
Yeah, so it's just averaged over all the tokens in the test corpus. And I'll talk a little bit about identifiers later on. So essentially, so what you see is that, this natural languages are kind of similar, and programming languages are all down here, pretty closely to each other, all quite repetitive, except Haskell looks a little bit different from the other programming languages, right? So just to show you that you have this sort of highly predictable nature of code as compared to English, and the difference is on the order of 4 to 5 bits. That means code is about 16 to 30 times, somewhere in that range, more predictable than natural language. Code is highly predictable, right? Okay, so why is this, right? So that's the main purpose of what I'm trying to make an argument about here. All right, so the alternative hypothesis, this is the one we like. This is the one we want to be true, right? We like this hypothesis, which is that, it's really that programming languages are harder to write and they're really harder to read. And since human beings are really interested in communication, they deal with this greater difficulty of programming languages by writing in a more repetitive fashion than even that they write in English, right? So they know that programmers are trying to communicate with other programmers in the presence of tigers and other dangerous beasts, and so they want the communication to be very efficient, and they know that programmers struggle to write and read code, so they just do it in a super repetitive fashion, even like 16 to 20 times more repetitive than English. So they write code that's as unsurprising as possible. Okay, so that's the alternative hypothesis. That's the one we like. Okay, and what's the null hypothesis? Well, no, it's nothing to do with that. It's just the nature of the language itself, right? So the language itself is, it's got terrible lexical properties, and the grammar is unambiguous and parsable left to right. No human language has the sort of same requirements that a compiler has, right? Human grammars are ambiguous. There's attachment problems, ordering problems, all sorts of crazy things you can do with human languages. And so, even professional linguists have trouble actually writing down the parse of some sentences, right? You have garden path sentences and, ambiguous attachments. I saw a man with a telescope. Did you see the man with the telescope, or did you see a man with, so there's all the stuff problems that exist in natural language. And so English doesn't have that. Okay, and so it's just because the lexical and syntactic structure of programs that creates this problem, and also that the programming language grammars are simple, right? So this is the null hypothesis, and we're going to reject it. I don't know how the null hypothesis feels about it, but we're going to reject it. Okay, all right. So two questions: what is the effect of keywords and operators in Java? And what is the effect of simpler Java grammar? So we're trying to account for this in some way with data and see whether the effect of these things is what makes the difference between programming languages and natural language, right? So try to find a way to control for these effects. Okay, so it's all experiments, and so that's what I'll be presenting today, right? Okay, so the alternative hypothesis is that it's really about difficulty, right? It's not about the syntax and the lexical properties, it's about difficulty. How do you account for this? Well, so we can go find English corpora that have some of the same properties, right? So law, technical manuals, right? We also have comments from version history repositories. It's not on this list, but it's on the data. And these are hard to write. It's hard to write a good lawsuit. Go look at the Mueller indictment. And so, it's the same sort of situation. It's a precise language where you have to communicate precisely, and yet the judge gives you 24 hours to write the thing, and you have to produce it, right? So it has that kind of in-between property between the full natural language and programming languages. So does the data also show this sort of intermediacy? So that's sort of a reasonable thing to do. And the same thing with technical manuals. And we threw in some domain-specific corpora like science fiction and Shakespeare to see whether it's the domain specificity that makes it the same. We also have recipes which are sort of instructional. So in the sense that code is instructional, recipes are also instructional. So to see if that is another reason why that code is so much more repetitive. Okay. The other thing is that we can look at is when you think about difficulty of production and consumption, English is a second language, right? So I speak a little German, and when I do, it usually I can see the pain on the people of native speakers. And I don't know much German, so I can just sort of say, where's the train station and this sort of stuff. So the words, I have very limited vocabulary, and so the constructions I put together, I have very limited notion of correct grammar. When I'm not speaking incorrect grammar, the correct grammar that I know is very limited set of laws. I know tecamolo, right? Temporal, causal. So I know that, and I can do that, but beyond that, I'm kind of stuck. So my German constructions are highly repetitive. So maybe that's what it is. So we can find English as second language corpora and look at that and see how it works. And finally, these are all things that we've already done. This is the last bit I'm going to talk about is ongoing work. I'm going to show you some graphs that we just created last week, 2 weeks ago. And this is basically asking the question, can we look at code and see whether programmers are actually, in fact, deliberately choosing from a very restricted palette? That is, they could implement things all sorts of ways, but they don't. They really pick a very restricted way of doing things. And that would sort of be additional evidence to support our theory. It's that people are doing this for ease of communication. Okay, so just to get started, so the first thing we're going to look at is what is the effect of keywords in Java. This is sort of the most obvious experiment. This is the one we started with. And so this is trying to reject the null hypothesis that it's the keywords that make code most predictable, right? So how do we do this? Well, so from the programming language corpus, it's easy. You remove all the keywords and all the operators, right? You take them all out. And you go, what's left behind is just identifiers, right? And look at that and see whether that has the same kind of highly repetitive property. What do you do with English? It turns out linguists have this situation covered. They have something called a closed, yes?
Can you remove the comments?
Yes. The comments are gone, yeah. So English, linguists have this thing called the closed category and open category. Closed category are things where we're not inventing any new ones, right? So most of these are fixed in most languages. What varies in English anyway are verbs, adverbs, pronouns, nouns, adjectives. Those things, we invent new ones all the time, and new meanings for existing ones and all that. But the rest of them, these things are fixed, right? So we can remove those from natural languages as well, and then we can see whether, after doing all this, is code still more predictable. Okay, so we did that, and we can reject the null hypothesis. So it doesn't really change things. In fact, the difference between code and English amplifies, right? So, and this is kind of really interesting because there's another thing I didn't go into much detail on, but code has a much bigger vocabulary for the same size corpus than English. And for obvious reasons, every module introduces new words, right? When I start a new paragraph, very unlikely I'm going to introduce something entirely new in there. But in code, it's a given and it's constant and it's quite prolific. Right? So despite that, the identifiers in code are much more repetitive. Yes?
Wouldn't these things that you remove be actually at the beginning of the graph, and so you just cut off like...
They're very frequent, yeah. They tend to be frequent, yeah. Mm-hmm. Keywords, yeah. And things like Java, Lang, whatever.
If you cut off left part of the graph, it still sort of looks the same, right?
Right, no, the slope has changed. It's become steeper. So in zip plot, it's roughly, log plots are roughly linear, the slope changes. So this difference becomes greater. So code is, the difference in repetitiveness becomes even more. And this is kind of what our theory suggests, is that because code is difficult to read, people will get more repetitive with it. Yes?
What's the proportion of closed category words in a corpus to open versus keywords to non-keywords in programs? So the ones that you've associated with closed, there's a
good question. I don't know the answer to that.
Normalization effect. You might be removing more from one category than the other.
this is proportion. I mean, this is a percent. So it is, in some sense, normalized on the y-axis. But that's a good question. I'll find out what that is. I don't know the answer to that. Okay, so and then you can do a language model on the open category words, and the entropy is more for everything, but the difference is accentuated, right, between code and English. Its difference goes up. So anyway, it's not the keywords, right? So that's not why code is more repetitive. Right, okay, so we ruled that out, and the next question is, what's the, I don't know, sorry about that, very faint. What's the effect of the simpler Java grammar as compared to English, right? So Java grammar is much simpler than English, and what is the effect of that, right? Okay, so the way we do that is that we try to account for both, and so you give the language model the benefit of knowing the parse. So in other words, the language model is now given all the information once about the parse of English and the parse of Java, right? So if the language model knows what the parse tree is, and the language model can capture all the context that's in the parse tree, then it's comparing English and Java on an equal footing. If it didn't have that, then the language model has to wrestle with the extra complexities and ambiguities and attachment difficulties that you have in English, but not in Java. Java is left to right parsable, so English is not. So if you don't give the parse tree, the language model has to wrestle with this. But if you give the tree explicitly and use a language model that has the ability to model long-distance dependencies, then the language model will essentially see both of them on an equal footing. It will be able to process the natural language and the English with complete syntactic information and see if there's really any difference. Okay, so what you would expect is if it's just the syntax, then the language model would find code in English equally predictable when it has all the complete syntax information. Okay, so that's the experimental approach we took here, right? Right, so in order to do this, of course, we needed a complete parsed corpus of English. Unfortunately, there is one available called the Penn Tree Bank. Damn it, you got to pay for it. So we did. It's several $1,000s, and so we bought it. and then you can take the tree and linearize it. I'll explain what we did. You linearize the tree. And then you apply a language model that is capable of modeling long-distance dependencies. So we used a gated recurrent neural network model because they can handle long-distance dependencies. And so that's what the Penn Tree Bank looks like. This is literally what you get when you buy the Penn Tree Bank, is this sort of text. And so this is, I'm not sure what the sentence is, but the bold things are the leaves. And essentially what we're trying to do with the language model is asking it, can you predict the next leaf given the context? Because that's what we're really interested in, is, right? We don't want the language model to do the other stuff. We wanted to see how well can you do at predicting the next leaf token in the corpus given the context that's already available to you, right? So if the language model can exploit the syntax and do a better job at predicting the leaves, that means the difference between code and English is really just in the syntax. Right, so that's English, and this is Java. I just got it out of Eclipse, no big deal here. And so then we look at the entropy of the terminal nodes, right, using a gated RNN. And so in theory, this should account for the tree structure and maybe reduce the difference. Well, in fact, it does reduce the difference. This is these are two are the Penn Tree Bank. I'll explain why the two in a second, and this is the Java one. And we'll look, what we did for comparison is using non-parametric effect size, which is a measure of the difference, right? So the measure of the difference between the original difference between English and Java models and the difference when you have the tree information, and look at the size of the difference between them. So the difference tells you how much, the difference between the differences tells you how much is explained by the tree itself. So why these two? Well, the reason is because there are many more non-terminals in the English corpus than there are in the Java corpus. Non-terminals meaning intermediate nodes, things like adjectival phrase, noun phrase, and so on, in the Penn Tree Bank. So we sort of simplified it to collapse certain categories that could be collapsed together. So we end up with the same number of non-terminals in Java and English. It's just a sort of experimental clarity to just make sure where the difference is coming from. As it turns out, it doesn't really make a difference. But it's just to kind of see whether the differences arise from the design of the parse tree. I mean, design parse trees many different ways. You could have different kinds of if statements if you want. If statements that do comparison, if statements that do equality, and we don't. Right? In English, they have a lot of these, linguists have made all these differences, and that increases the number of non-terminals, and we sort of collapse them just as an experimental condition to see if that's where the effect we're observing comes from. Okay, so the difference in the difference of the effect size between the two cases is without syntactic information is 0.414. So that's a difference between Java and natural language. And when you account for syntax, the difference drops. So there's a small difference. It's about a 15% difference. So according to this particular experimental study anyway, about 15% of the difference between Java and English language models is explained by the syntax. The rest of it is all something else, right? So that's sort of the conclusion one can draw from this. All right. Okay, so this is the non-parametric Wilcox effect size because the distributions don't really look very normal. Right. Okay. And so yes, there is an effect, but it's not a particularly strong effect. So the language kind of the syntax does make some difference. All right. The next thing we looked at is the language difficulty. So is it the difficulty of code as opposed to English that explains why code is written so repetitively, right? So to do this, we looked at a bunch of different technical or hard corpora, commit logs, tech manuals, a law corpus, science fiction, Shakespeare, and so on. And then also English as a second language to see what the difference is. And so the first thing I'll show you is comparing the repetitiveness in these different corpora. So this is sort of interesting, right? So the top one is Java. We didn't do other languages in this plot. So the top line is programming languages. It still dominates. Repetitiveness in a programming language still dominates. It's the most repetitive thing we have. This cluster here is Shakespeare, science fiction, and Brown. This cluster here. They're sort of like non-technical, non-imperative style languages. And in the middle, we have law, NASA, and recipes, right? These three are sort of in between code and natural language. So this sort of, again, supports our hypothesis that the repetitiveness is really coming from the style of language in which people choose to write, right? So all these three here have, you look at them, they're like, the NASA is basically NASA instruction manuals. It's like, they're called NASA directives. They report how you're supposed to build products for NASA. They're instructions to their contractors. This is recipes, also instructional. And law is, United States code. So all these have this desire to be for precise communication, right? The communication has to be precise. You don't want any misunderstanding, right? And so as a result, the way people choose to express themselves is more like code than it is like plain English. So again, suggesting that it's deliberate choice by the writers to put these between the two extremes. That is, it's not really anything to do with the nature of the syntax itself. And this again, is borne out in the models. You can see the general corpora kind of here at the ends, and the code down here, and the other things here. Commit log is an interesting case, and you can see in the previous plot as well, the commit logs actually crosses over between two different regimes. And this somewhat has to do with some commits being either automatically generated. We try to remove that as much as we could, but other ones are very rote. They're kind of like, almost apparently produced by humans, but highly repetitive. And some are more descriptive. So it sort of crosses two regimes. And you can see that commits, in entropy actually looks more like straight natural language than it does like NASA or recipes or law. So again, sort of supporting this sort of alternative hypothesis we've been trying to argue for. Right, and the last sort of set of corpus experiments that we did is treating English as a second language, right? So we were able to find two different corpora. One is second language learners in Korea, and the other is second language learners in mainland China. And so again, you see the same sort of interesting thing. The bottom is general English, the brown corpus, the top is code. And between the two is where you'd expect the second language corpora to be, and that's exactly where they are, right? So again, sort of reflecting the argument that the more difficult it is to produce, the more repetitive you get. Okay. And when you look at the models of these things, again, you observe the same thing, right? So this is the Korean second language corpus. This is the Chinese second language corpus. And you can see, again, they're sort of between the brown corpus and the Java corpus. Yes?
Just a basic question maybe about this. If you add noise to corpus, what happens with the curves? Just
It'll flatten them out. You know, so noise, assuming the noise is, depending on how you generate it, if you generate it uniformly at random.
If you add noise to second language corpus, does it approach the brown corpus?
It should. I mean, if your noise is uniformly generated, right, you're generating tokens at uniform thing, then you'll flatten out the.
So I guess what I'm wondering is whether the natural language is partly, if it's not a second language where you're focused on communicating content, then it's not just noise from the purpose of communicating the main intent, as opposed to artistic beauty and some other subtext-like things.
In fact, I would say it's like noise resistance, right? I mean, so you communicate in a way that allows your listener to pick you up and understand you, even if there's, if the listener is not fully paying attention and the listener is distracted and there's noise in the environment, right? It's the idea of, the reason why speech recognition works is because even if you hear a noisy signal, when you're trying to do the conditional distribution of the actual word given the noisy signal, you don't have that many different choices. The language model tells you yeah, it couldn't be, the example I like is if somebody said European Central Bush, right? You're not going to say, okay, that's a bush, European Central Bush. No, you're going to say, most of the time the language model tells me what comes after European Central is bank, right? So you figure that out, right? So, so it helps you, the predictability helps you disambiguate, yeah.
Just to come back on that, and slightly, it seems that there is a very different kind of activity going on with natural language. You're often trying to use language in a creative way, like it's not just communicative.
Not often.
That seems to be intention with the other, but it's always minimizing its kind of.
Well, I think that's the point is.
Free channel in order to be very creative within that.
So you're saying that that people are actually, in fact, very often very creative with natural language.
Yeah, intentionally so.
I don't think the data supports that.
Okay.
I like to think that we're creative in the way we talk, but.
Like when you're programming, for example, if you name a concept, you pretty much have to use the same word for that concept you're trying to name it. Whereas often people intentionally choose a different name to have a slightly different inflection of meaning. And you're saying the evidence doesn't support that.
That's the weird thing. People do choose names. I mean, the vocabulary proliferation is a real problem for language modeling in code. But if you do handle it appropriately, it's still very repetitive. It's still 1.2 bits, 1.4 bits per token, even in the presence of exploding vocabularies. Right? And if you figure out how to do manage vocabulary in, for example, in deep models, which we can't, maybe it'll be even better. But so far, we don't know how to do that. Right? Okay. So here we are, our alternative hypothesis and the woefully rejected null hypothesis. Right, and now, so I'm not sure we're completely proven this yet, and we're still at it. But I think we found more evidence to support this than when we started with. I hope I've made that case. Right. Okay. So what does this all mean? This is the sort of last set of experiments we're doing right now. It's Casey's thesis, and he's getting ready to wrap up. So what does this mean? This alternative hypothesis, right? So what this means is that given a computation that you tell a programmer to implement, you tell them to pop up a window and get some data, or assemble a packet, encrypt it, and send it off, or do something like that. Given a programmer a task like this, she is going to favor one particular implementation, right? That's what the argument is saying, right? So given a set of implementations which are equivalent, semantically equivalent, for a particular computation, then if you have a good language model, then the probability assigned by the language model to, I hope I didn't screw up the animation on this. Okay. Damn it. Maybe I'll just escape out of this. And anyway, Sorry, I can't show. It's not that complicated. I'm just saying the language model is going to assign one of those implementations a much higher probability than the rest of them, right? So, and this, this is something we can check. We can set this up as a null hypothesis, and we can gather data and, get a p-value out of this, right? This particular research question, right? So we can do this, and we did. Good. So, right, so how do we do this, right? So this is the general scheme that we're in the middle of now. We've done a bunch of experiments, and we're doing more. The general scheme is you estimate a language model over a large corpus. You've got 500 million tokens now. It's not a problem. You've got a very efficient language models. By the way, give SLP Core a try. It works really well, and a lot of people are using it right now, including some companies. Right, okay, so using this language model, you measure the entropy of a natural program, something you find in the wild, right? And you take something that's not in the training corpus. And it's trickier than it sounds because there's a lot of copied, pasted code everywhere. You've got to be somewhat careful with this, all right? So you take something like this, and then what you do is you apply meaning-preserving transform to S, producing clones that behave identically, right? Lots of these clones, right? And you use the language model to measure the entropy of the original program S and the mutated ones, right? Okay, so if you do that, then the null hypothesis is that there's no difference. That is, a programmer, the language model says, any of these a programmer could write. They all look good to me, right? Language model doesn't see a difference. But if the language model says that one, the original one that you mutated into all these, that one I like. The rest of them, I don't know where that came from. No human being would ever write this, right? So if you believe that the language model is sort of, in some sense, capturing what people prefer, right? And apparently they do because they're down to 1.4 bits per token, right? Then the language model should be able to answer this question, whether these equivalent ways of writing are acceptable or not. Is that clear? Yes?
I'm wondering what kind of transformation.
Okay. Right, okay. Right, so what is that? All right, so we tried a bunch of things, right? So the obvious one, easy one, which is the first one we did, is commutative operators, plus and multiply. I know, they don't really commute in floating point, but anyway, we did that. Superfluous parentheses removal, yes, there are superfluous parentheses all over code. Superfluous parentheses insertion, sometimes you can add them and it doesn't really change anything, but you can put them in there. Associativity, and independent statement reordering. So these things are still, this is currently ongoing, and this one we're having the devil of a time trying to figure out a suitable tooling framework to do this at scale. But anybody has any ideas, I'd appreciate hearing about it. But so that's what we're doing, right? And I'll just present the results from the first one, which is all that we did, right? Okay, so so here we are, right? So this is the original code, and this is the population of code that's been transformed. And what you see is, it's a statistically significant effect, and the effect size, roughly speaking, is around 1.25 bits. Now, this is underestimating the difference because we did a foolish thing. We're trying to fix that right now. Basically, this is the average entropy per token in the line that was mutated, which is the wrong way to do it. What you should really do is compare the tokens that were changed and not ignore everything else, right? So if you have A plus B times a bunch of other stuff, method call, whatever, what you really care about is when you change A plus B to B plus A, what does it change in the entropy of A plus B and B plus A? That's all we really should look at. This is the whole line. Anyway, it's 1.25 bits, which is about 2.5 times less likely, right, when you mutate it, right? So what this means essentially is that people are deliberately choosing to write things a certain way. I mean, it's not that surprising in retrospect. I mean, everybody writes A plus 1, right? Nobody writes 1 plus A, right? Or A plus B, nobody writes B plus A. They go in alphabetical order. So there are certain sort of preferred ways of writing. And the original argument, again, that we made to start with, is when you're reading code or writing it, you just do it the least effort possible. And the least effort possible is the same crap that you've seen a million times before. You just spout the same thing because it comes easily to your fingers, and whoever's reading it, it's easy for them too, right? Okay, and here's another little plot that's sort of interesting. This requires a little explanation. The y-axis is the change in entropy when you mutate, and the positive change is here. That means it becomes less likely when you mutate it. And this is negative change, which means it becomes more likely when you mutate it. That is, the entropy drops. The model likes it better when you mutate it. And the x-axis is the original per token line entropy. And we call this the Death Star plot. And this is the same plot we see for every mutation. And it's not that complicated. What it's basically saying is that the lower the entropy, right, the more the model likes it, leave it the hell alone, right? Don't mess with it, because that's the way programmers like it, right? If you change it, they're not going to like it. As the entropy increases, it's less clear, right? So it's less clear what happens. This may be because some programmer wrote it a weird way. Maybe they like it that way. Maybe it's unusual. It's less clear what the mutation does. Also, the other thing that's interesting is that local effects matter. So we have different ways of tuning the model to local files and local projects. So when you tune a model to the local file and projects, the effect size increases. So that means there are strong local preferences which are different from global preferences, right? So I'm not sure what that means exactly, but so this is also something we see in every one of those plots. So finally, all right. So the purpose of this whole exercise set of experiments was when we glibly wrote this stuff saying code is natural, we didn't really have a case that was actually because of the same human imperatives. I think now we sort of made a stronger case for why that is. So this is a primarily scientific endeavor, but one thing I will say is, one thing that already came out of this is that we found that we can improve the performance of the language models by a little bit, about 5 to 10%, by just looking at the open category tokens. So if you mix the open category model with the full model, we get about 5 to 6% improvement in performance for the code prediction task. So it is primarily a scientific endeavor, but there are some potential applications of this work. Thank you.
Before we said at the beginning, I missed it, but how do you quantify the repetitiveness of, so we look at the zips?
Yeah, the standard, if you want a measure of it, you could do various things, but the easiest thing is just look at cross entropy with the language model. Yes.
What do you think are the implications of this for programming language designers?
That's a good question. I don't know. I don't really know. I mean, maybe we should go back to COBOL. It's really about communication. Then maybe we should tell stories to each other instead of writing highly precise functional programs. I don't know.
Yeah, another thing I was wondering about was correctness, right? So do you see any possible connection between how natural, what piece of code looks like, and the likely, the ease of achieving a correct program?
Well, I mean, indirectly. I mean, so we had this paper a few years ago where we just used language models to predict faulty lines of code, and it works about as well as find bugs. It's different in the sense that all the language model will tell you, I don't like that line, it looks weird, whereas find bugs actually tells you why it doesn't like it. But if you just review those lines, the defect rate in those lines that are highly entropic are about the same as find bugs warning lines. So that's maybe an indication, but I'm not sure that's what you're asking.
No, maybe we could talk about it.
Okay. Yes?
Thinking the other extreme, if we get the high-level programming language already more repetitive than human language, if we compile the result into binary form and measure the entropy of the binary, which is meant for machines to read, would that be even more repetitive?
We haven't done that, but I've heard I've heard that from. Yeah, I've heard that. Yeah, that binary is also very repetitive. Yeah.
But more repetitive, how we haven't got this
I don't know, but I've heard that language models work for binaries.
for binaries.
Yeah. Yes.
So you have a slide where you're comparing the entropy of English and the entropy of identifiers.
Entropy of what? I'm sorry, what was the first one?
English and identifiers.
English identifiers, yeah. So English open category words, right.
Yeah, so the thing is, though, like as you said, there's like big proliferation of identifier names in like Java in any programming language.
Yeah.
Doesn't that skew the results a bit? Because like in the LSTM is gonna mainly assign a known word probability, which is gonna be like quite high.
That's
diagrams, like we do a lot of smoothing there.
Yeah, that's a great question. So the question you're asking is LSTMs, you have to prune the vocabulary down because the softmax layer in the output can't handle huge vocabularies. Yeah, exactly. So the experiment I showed you comparing open category words in English with code identifiers, that wasn't using LSTM. So that was using cache models with unlimited vocabulary.
Yeah, I see. Okay.
Right. So that does come into play when we look at syntax trees. Yes, it does. Right. That is a factor. Yeah.
There are no further questions. Then let's thank Prem again.